Ok. Non inizio a contare. Ok. Hello, everybody. Good evening, and welcome to the first pitch, the PhD pitch of 2022. My name is Andrea Bontempi, and I'm new treasurer of Icp student branch of Politecnico di Torino. I'm very happy to present this pitch, and it's my pleasure because this is a moment where we can share our research, our work with our colleagues and other members of the university, and maybe learn something new and something different. Before we start, I want to say that it's possible to type the question on the platform, and at the end of each speech, I will read the question to the speaker. So feel free to type the question on the platform. We can start with the first speaker. Stefano Calvo received his master's degree in 2020 in nanotechnologies for ICTs from Politecnico di Torino. He is currently a PhD student at the Department of Electronics and Telecommunication of Politecnico di Torino, in collaboration with Vodafone Italia, and his research field is smart agriculture. His work deals with development of low-cost and low-power device for continuous monitoring crops. Today, he presents a talk about development of low-power and low-cost electronic system for smart agriculture. So, Stefano, you can share your presentation.
Okay. Oh, sorry. Sorry, Okay, can you hear me and can you see the presentation correctly?
Yes, Stefano.
Okay. Good evening. I'm Stefano Calvo. I am a PhD student, currently enrolled in the first year. My research field concerns smart agriculture, and this is the main topic I will discuss with you today. My presentation will touch three main topics. At first, I will show you the importance of the implementation of smart agriculture. Then I will present you some examples of applications. And then at the end, I will discuss with you my work that deals with STEM impedance monitoring. In the last century, world population growth rate has reached its peak. As you can see in the graph, it was reached in the 60s, yeah. And then this rate is due down. Nevertheless, it has been estimated that by the end of this century, the world population will reach the number of 10 billion. And a question is arising. How can we feed them all? Food production has a huge environmental impact. As you can see in this graph that I took from our world in data, that is very, very punctual on with its analysis, more than a quarter of the total greenhouse gas emission of is due to food production. Moreover, 70% of the total freshwater withdrawals and 78% of the release of pollutants in the soil are due to food production. These numbers are destined to increase because of world population growth. Together with the increase of demand of food, Another important aspect is threatening severely food security, and that is the land desertification. As we know, climate change is causing an increase of temperature around the world and at the same time a reduction of precipitation. This means that more and more dry lands are turning into desert, and the ones that are not directly affected by desertification are getting less and less fertile. To give you an idea of the impact of this effect, more than 5 million square kilometer of drylands have already turned into desert due to anthropogenic climate change. To give you an idea, it is roughly 15 times the extension of Italy. Something must change. Smart agriculture aims at solving this problem by reducing the footprint of food production and at the same time increase the harvest, the yields. So, and this may be achieved through two different approaches. The first one is called the indirect approach, and the second one we can call it the direct approach. In the indirect analysis, the systems that are spread into the fields that are meant to merge they're meant to be merged with the knowledge, with the farming knowledge, are focus their attention mainly on the environment surrounding crops. It means that, for example, as you can see in this picture, it is possible to spread into the fields weather stations. Those weather stations perform most of all, above all, weather forecasts. And, for example, they could provide valuable information to reduce the amount of water used into the fields. And it is a double effect since this reduction has a double effect since it is possible to reduce the total amount of water used to grow crops. And at the same time, since water is spread with pumps that are electrically powered, it will reduce the carbon footprint of food production. Moreover, as I show you here, indirect analysis could involve even more complex systems, and this is the example that I show you here in the picture, where this box contains a infrared camera that is pointed toward crops and soil that detects pests in their early stages. This is possible thanks to the heat that these living beings product, and thanks to a machine learning based algorithm, the camera is able to recognize pests with respect to normal bugs that are not a threat for crops. This camera is very useful since it is possible to detect pests before they start ruining crops, and so it is possible to reduce the amount of pesticide needed to get rid of them, and so it reduces the pollutants released into the soil. Unfortunately, indirect analysis is not enough, and often it is more interesting and more useful to implement the so-called direct crops analysis or direct analysis. It deals with the analysis of quantities that are proper of plants. For example, in my work, I deal with the analysis of stem electrical impedance. So I perform an analysis of a small portion of a plant stem to get its impedance analysis. In the picture I reported here, there is a schematic of the system that we developed to control 4 tobacco plants at the same time. It is a very simple system. It is basically based on a LabVIEW script that runs on a bench on a laptop, and it controls a bench impedance analyzer that through a multiplexing circuit, it can control 4 different crops. for different plants that are subjected to different kind of stresses. For example, one is affected by water stress. Another one is not illuminated properly, and those are the two main stresses that we perform on plants. We discovered that stem electrical impedance reacts to different kind of external stimuli. For example, in the picture I show you here, it is very clear that impedance reacts to the presence of light impinging on the plants. As you can see in the graph, the blue line reflects the behavior of impinging light on the leaves, where we placed a small sensor to detect it, and where when there are its peaks, both impedance modulus and phase react in a different way. As you can see, the modulus reaches its minima when light is maxima, and vice versa, the phase rises when the light is at this maximum. This behavior may be due to the fact that when photosynthesis is performed, so when light impinges on leaves, roots and leaves exchange substances through two channels that run along the stem. Those two channels, we can say that they open when the photosynthesis is performed, and it makes the stem more these two channels make the stem more conductive. Another important feature that we discovered that plant stem or trunk have is that they can be thought as conductive channels. So they can propagate an electronic signal within their stem or their trunk. In the picture, you can see a prunus bianco, that is a small tree that with a thin trunk that has two couples of electrodes inserted in it. The top two one that you can see here are the end of the transmitting system, while the bottom couple is a receiving system. The transmitting system injected a specific wave an alternating signal that the bottom couple of electrodes received and collected. We discovered that there is a specific range of frequency in which the communication within the stem reaches its optimal performances, and we discovered that this modulation of the communication is modulated by the stem electrical impedance, or in this case by the trunk. And therefore, it is possible to analyze the propagation inside the modulation of the signal along the trunk to gather valuable information about the stem or the trunk impedance, and ultimately regarding its health status. Unfortunately, the two systems that I showed you before are not feasible, nor are not feasible to be implemented on the fields, because they are really complex. They need to be managed by an engineer, basically, because it is not very. It's not easy to make them work, and moreover, they are really expensive and power consuming. Therefore, we are trying to develop a system that relies only on renewable resources, and it is a low complexity. Therefore, it is easier to manage, and it is low power and eco-friendly, and it is meant to last for a long period of time, and this length depends on the crops in which it will be implemented. As you can see, the system could be schematized in 4 different blocks. The first one deal with the energy, and there is an harvester that is basically used to exploit renewable resources, and a storage element that ensures power supply when the harvester is not working. But because, as you may know, for example, regarding solar cells, it's not possible to get power from them 24/7. For example, right now there is no light on the there is no environmental light, so it wouldn't be possible to power the system. And then there is this power management unit that its main goal is to lower the consumptions and at the same time performing measurements by powering a square wave generator. The real core of this system is the square wave generator, since it is in its feedback loop there is the plant stem. As you know, when resistance or impedance is placed as a feedback of a square wave generator, its frequency will directly depend on the impedance itself. And it is known that it is much easier to read a frequency with respect to an impedance. Therefore, with this system, it will be possible to perform analysis 24/7 and spread those systems that will we expect it to be really small, cheap, and in the future they could be made on more eco-friendly substrates with respect to silicon. And it is possible to monitor a whole field at the same time. Unfortunately, the results that we got by now, up to now, are a bit contradictory in terms of the impedance behavior, but really promising with respect to feasibility and, above all, system autonomy. Thank you for your attention. I'm willing to answer any questions that may arise.
Thank you, Stefano, for your presentation. We have two questions from public. The first is, among direct and indirect analysis, which is more cost effective? Also, does both analyses take the same time to complete?
Okay, as always, it depends on the implementation. It is surely up to now, systems performing indirect analysis are much more advanced and a lot of them are off the shelf. For example, the weather station that I showed you before is it is possible to actually buy it. If you go on the website I linked you in the source, you can actually buy it. On the other hand, sorry, what was the first part of the question? I forgot.
Also, does both analyses take the same time to complete?
Again, it depends on the applications. For example, the system that we are developing is meant to be very quick, and since it performs just one analysis, so it basically reads the frequency and sends it to a base unit where it will be analyzed. Weather forecasts, I imagine, that are more complex, since it must integrate different kinds of parameters, and as you know, it should solve the complex systems of partial differential equation to perform weather forecasts. So up to now, the more complete and performing systems are, I would say that they are the indirect ones. They are more ready to be implemented, but I think that some of their limits will be overcome by direct analysis.
Okay. And the second question is, does in vivo stem impedance method affect the measurements? If yes, what action can be taken to reduce the error?
Okay, in vivo measurements could be affected by, in vivo measurements could be disturbed by the plant itself, and in fact we discovered that the kind of electrode that is inserted into the plant will really affect the analysis. We discovered that the smaller and the thinner actually the electrode is, the less effect we will see on the measurements. Right now, we are using surgical needles that has then they have a section of 0.4 millimeter, and moreover, they are surrounded by conductive and biocompatible film, and it is basically the same one that is used in hospitalization in hospitals to take blood from veins. So it's right now we think that that issue could be solved, but yes, in principle it could affect analysis.
Okay, and I want to say that do you think that the direct measurement, so the impedance, can replace the indirect measurement, or is better to use together to have the best performance?
Okay, for this I can answer for what concerns my work. We discovered that plant stem impedance reacts to external stimuli such as weather changes or water stress, and we are now trying to get a sufficient amount of data to get rid of the indirect analysis that we performed. I showed you that we performed the analysis of the impinging light. If we collect enough data and we are actually trying to manipulate it with a machine learning algorithm, we will be hopefully able to get rid of the complex and power-consuming part of the system that is basically the sensor node that collects data from the environment, and rely exclusively on the stem impedance analysis. Hopefully, that's what we are trying to do right now.
Thank you, Stefano. Very clear. So,
thank you.
If there are no other questions, we can proceed with the second speaker. So, thank you, Stefano, for your presentation. Eva Catoggio received a master's degree in electronic engineering from Politecnico di Torino in 2019. She is currently a PhD student at the Department of Electronic and Telecommunication of Politecnico di Torino, and her research field is electronic device modeling and simulation for analog application. And today she presents a talk about efficient TCAD large-signal temperature-dependent variability analysis of a FinFET power amplifier.
Can you hear me?
Yes.
Okay. Okay. Hi, everyone. I'm Eva Catoggio, and today I'm going to present the efficient TCAD temperature-dependent analysis of a FinFET power amplifier in large signal conditions. The most common power devices in RF applications are FinFET, MOSFET, and but also new emerging technologies such as tunnel or ferroelectric FETs. In the last years, there is a growing interest for exploiting FinFET technology in the millimeter wave frequency ranges, especially with reference to 5G applications, thanks to their high cutoff frequency and their lower cost. The miniaturization of electron devices leads to a significant technological spread, the impact of parasitics, and a difficult thermal management. This one can give some self-fitting problems in static conditions or harmonic distortion in the dynamic case. In this perspective, there is the need to develop a temperature-dependent physics-based sensitivity analysis in both static and dynamic conditions. RF and microwave power devices typically used for large signal simulations require a dynamic TCAD analysis. For this reason, we have introduced a numerically efficient technique for thermal TCAD analysis through the development of an in-house two-dimensional simulator. The simulator is composed of a drift diffusion model, which includes some mobility models, the self-heating model, and the thermionic emission model for heterostructures. These ones are strongly dependent on temperature variations. Moreover, quantum effects are taken into account through the density gradient model, whose implementation is ongoing at present. Moreover, there is in our code the harmonic balance technique, which is used for large signal simulations. In the code, the device is considered as embedded into an external lumped thermal resistance, through which heat is dissipated towards a heat sink at temperature T0. The device temperature T is uniform in all the mesh nodes, and we can divide two possible cases. In the first case, we don't have a thermal resistance, and the device temperature is always equal to T0, so it is externally varied with the heatsink temperature. This case has been implemented in both DC and large signal conditions, while the second case considers a thermal resistance. Therefore, the device temperature is higher than T0 because of the heat dissipation process. The last case is implemented only in DC condition at present. Oh, just a second. Okay. Okay, with this code, we want to calculate the device response to temperature variations with respect to a cold status, which is typically 300 Kelvin. Or physical or technological parameter variations with respect to a nominal value, and finally concurrent temperature and parameter variations together. The drift diffusion code is able to perform this analysis through an incremental approach, which consists of repeated simulations at each temperature T, then repeated simulation at each parameter P, and finally, for concurrent variations, we have a total number of simulations equal to the product N times M. So this is a time-consuming procedure that can be overcome through an efficient thermal variability analysis based on the so-called Green's function approach. I present the Green's function approach starting from the temperature-dependent analysis in large signal conditions. So in this case, we have we don't have a thermal resistance, and the device temperature is a parameter that can be varied with T0. In particular, we consider small variations of temperature in order to have a linear perturbation of the device nominal working point that is in this case periodically time varying. So we consider the device physical models and we linearize them around the cold temperature in order to find the Green's function. this is the expression of the linearization where we can identify the local source term, which is the product between the derivative of the device physical model with respect to temperature and the delta, the temperature variation. Now we can calculate the induced perturbation at the terminal currents through a convolution integral that involves the variation sources and uses the Green's function as a kernel. This linearized approach gives an advantage over repeated temperature-dependent simulations because the Green's functions can be efficiently calculated and they need to be estimated only once at cold temperature, so we don't need repeated simulations. Now we consider a concurrent variation of a parameter, physical or technological, so we can use the previously calculated Green's functions and then calculate two convolution integrals. The first involves the variation sources with respect to temperature. The second involves the variation sources with respect to the parameter. These current variations are found considering the device in short circuit conditions, but our device has an external load, so the final delta current due to temperature and parameter variations is given by this expression. To conclude, we have a self-fitting analysis in DC conditions. So we consider a thermal resistance, and we have a temperature increase due to self-fitting that can be represented by this expression, the first expression, where we can see the final temperature device and the dissipated power. The linearization of this expression leads to a final formula that gives the terminal current calculated at the final temperature and involves the cold terminal current E0, K, and S, which is the thermal sensitivity. The thermal sensitivity is the delta current due to the temperature variation, which is obviously calculated using the Green's function. Our case study is a FinFET power amplifier with 45 nanometers gate length and 25 nanometers H-fin. We simulate a multi-finger device, so we have 10 fingers of 30 fins each. And we simulate a class A power amplifier with an operating frequency of 70 gigahertz. We have an optimum calculated an optimum load for the fundamental frequency, and the harmonic balance technique is performed with 10 harmonics. Our aim is to validate the GF approach, varying the temperature up to 50 Kelvin and varying parameter, which is the doping concentration in the source and drain regions of 15%. And finally, we use two different thermal resistances to see the effect of self-heating. This is the first result in DC condition with just a temperature variation. We see that the output characteristics show an excellent agreement between the Green's function solution and the reference solution. The reference solution is the one obtained through the incremental approach. And we can notice how the current is decreased due to the temperature increase above threshold. Here we have the result of the self-fitting analysis, always in DC conditions, and with two different thermal resistances. There is a reduction of the drain current, even in this case, but due to self-heating. and there is a higher reduction when the thermal resistance is bigger. The GF approach is worse in the case of the red curve, because in this case there is a stronger temperature increase. In fact, temperature reaches, it can be noticed from on the right-hand side, temperature reaches 370 Kelvin in this case. Here we have the stage temperature dependency, but in large signal conditions. So we can notice that even in this case there is an excellent agreement, and the solution obtained with the Green's function approach is as the simulation time reduced with respect to the other one. It's about 20% of the incremental simulation, and there is a reduced swing of the dynamic load lines, which are represented in the plot. There is a reduced swing due to the effect of the temperature, which produces a mobility degradation and a consequent increase of the knee voltage. Now we add a concurrent variation of the doping in the source and drain regions, and in this plot we can see the dynamic load lines, which are calculated with negligible time overhead. Moreover, doping variations further affect the parasitic resistances of the device, and we can notice that the lower is the doping, the more is the compression of the dynamic load line. Here we can go on with the power performance. On the left, there is we can notice a degradation of the output power with a temperature increase, while on the right there is the available gain, which is not only affected by the temperature increase, but also by the doping variation, especially in the compression region, so for high values of the input power. To conclude, there is the stage efficiency of the power amplifier. In particular, we have on the left, we have the drain efficiency, which is reduced by the temperature increase, but not very affected by the doping variations. On the left, we can notice the delta efficiency, and we can see that for low values of the input power, we have a higher efficiency with a lower doping, while in compression we have an opposite behavior. So to conclude, we can say that FinFET technology is promising for millimeter wave applications, and that our TCAD approach based on Green's functions is not only accurate but also a mature technique for the assessment of nonlinear circuits. And finally, we have validated this approach in two conditions. In these two conditions, we have seen that the drain current was strongly reduced by the temperature increase, especially with a thermal resistance, while in large signal simulations, the thermal gradation affects all the operating conditions and dominates always over the doping sensitivity. A future work can be the extension of the self-fitting analysis to the large signal conditions. Thank you for the attention.
Thank you, Eva, for your presentation. So we can pass to the question. The first is the temperature sensitive simulator limited to a specific device models only? Can you hear me?
Sorry, I can't hear you.
Okay,
no.
Sorry, I repeat. Is the temperature sensitive simulator limited to a specific device model only?
If it's limited to a specific device?
Yes, specific device models.
Can you hear me?
Yes.
Okay. Actually, no. It's not limited in the sense that you can include in your code the model you prefer, but we have at present we have only the diffusion model, and for now we want to add some different models to this one.
Okay, thank you. And the second question is how much the results vary for one simulation as compared to the NM approach? In other words, how much the accuracy is affected as compared to the NM?
Sorry, can you repeat?
Yes. How much the results vary for one simulation as compared to the N per M approach? Is other
okay. With the N per.
I finished the question.
Oh, sorry.
In other words, how much the accuracy is affected as compared to the N per M? Okay, this is the question.
Okay. The incremental procedure with the N per M simulations is not very efficient because the total simulation time, for example, for 5 temperatures is like 20 hours simulation. So with the Green's function approach, we have only the 20% of the simulation time, so more or less 4 or 5 hours. So this is the main advantage in this sense. Hello? Yes. Okay. But I answered. I hope you can. Okay.
Oh, sorry.
Okay.
Okay. I repeat the question.
No, I answered.
At the okay. You answered the last question. Do you hear me before? No?
Yes.
Okay.
Okay.
Okay, the final question is, which interface does the simulator have? Does it accept a standard SPICE netlist? Will it be publicly available?
The final part of the question, can you repeat, please?
Yes. Will it be publicly available?
Okay, I don't know if I understand the question, but our simulator is on MATLAB, so there is no. This is the interface in our case, but there are other simulators, commercial simulators. Our in-house simulator is on MATLAB.
Okay, and we have a last question, other one.
Yes.
Thanks for your presentation. My question is, can this study be extended to the other FET technology, such as GAFET technologies and so on? Thank you from YouTube.
Yes, it can be extended to other technologies, but it's necessary to add some models. For example, for the GAFET, you need the GAN. Okay, maybe GAFET. You need other models to describe the structures, but it's possible to do it.
Okay. Thank you, Eva, and sorry for the problem.
No. You're welcome.
So the question is finished, so thank you again, and we can I can present the last speaker. Thomas Favale received his master's degree in computer engineering, specializing in the network branch in 2019 at Politecnico di Torino. From May 2019, he started a PhD at Politecnico di Torino under the supervision of Professor Marco Meglia, joining the Center for Smart Data. His research activity has been initially focused on the problem of anonymization of network traffic. He developed α-Mon, a tool capable of applying a new form of real-time anonymization for big data analysis project for the evaluation of IoT device behavior, with the objective of improve knowledge and technology on a continuous evolving field. He is currently involved in the study of malicious traffic on darknets and honeypots to enhance network security. Today, he presents a talk about α-Mon, traffic anonymizer for passive monitoring.
Hello, Andrea. Thank you for your kind introduction. I'm trying to share my screen now. I hope you can see now the presentation. So today I would like to drive you in a section of my research activity, which is based on the traffic anonymization. So a technique that helps enhancing privacy for the user on the network. This project has led to the development of a novel tool, which is called α-Mon, and this activity has been brought out thanks to the collaboration of the Smart Data at Polito Data Center. In order to explain and introduce you to this project, I would like to follow these steps. So I would like, first of all, to introduce you to the concept of traffic monitoring, why we're doing this, what is changing due to the new regulations, which are the common approaches to prevent information disclosure, and then I would like to talk about the alpha-anonymity and α-Mon, so our novelty that we want to introduce to the world, and finally I would like to draw some conclusion and possibly have some discussions with you. So what is traffic measurements? Actually, nowadays we try to collect network traffic because they are so important in order to enhance cybersecurity and perform some traffic management. The problem is that by keeping these packets, we are keeping also sensitive information about the users, and so this could be kind of scary. So in the last years, the European government has started to introduce new regulation in order to prevent threatening the user privacy, and so our project sits inside this context. Which are the common approaches? In order to achieve this object, the main activity that has been performed is the anonymization. So it means that we would like to obfuscate sensitive information inside database and so on. There are many algorithms that does this sort of stuff. One of the most important is the kernel anonymity, which means that given a certain database, we want to let them be key anonymous. So let's be at least k entries indistinguishable one another. The problem with these algorithms is that they need to have access to a complete dataset, a scenario in which we cannot sit. In fact, we would like to have an approach which is in a streaming fashion. And so here we would like to introduce the alpha anonymity, a new way to anonymize information. As I could introduce before, it sits with strict requirements. First of all, the dataset is not available, as I said before. Then it should work on real time with zero delay and should be so fast in order to be scalable and applicable on a multiple gigabit environment. So what's the real problem here? The real problem is that, as I said before, the algorithms that are used today are based on the access on a complete dataset or batches of it. We would like to do it in a completely streaming fashion with no buffering and zero delay. As shown in this video, I think it is not so fast, but as the car arrives, the tire changes and it goes out. So at the same time the packet should arrive, everything should be anonymized and go out without the waiting for other stuff to come. It's not necessary. Here in this slide, there are some stuff a bit theoretical. I would like to go fast on these and just explain one concept that would be easier to understand in the next slide. So an alpha private quasi-identifier, so a name, something that is subject to the privacy of the user, is a value that is observed at a certain time t, which is associated to less than alpha data subjects in the past delta t time interval. What does it mean? It means that a given information can be considered private if it is related to less than alpha users in the past delta t time that can be defined by the user. This means that, for example, there are many users that are searching for a given name, for example, private.com, and we have set the threshold of alpha equal to 3. Delta t is not so important. It can be any time interval that you prefer. Assuming that first user arrive, we set is delta t, and since we have a counter that sits at 1 here, we are under threshold, and so the information should be private in this sense. The same thing happens if a new user arrives. So here, there is a new user, we increment the counter, we are still under threshold, and we set the delta t time interval. In this case, assuming that the 2 users comes again, for example, user 2, we don't increment the interval, the counter, sorry, because we already seen the user in its time interval. So we just need to update it and leave the information private. And the same thing happens if user 1 comes again. We update the delta t time interval and information is still private. Assuming that now a new user arrives, now this user can let the counter increase, reach the value alpha equal to 3, which was our threshold. The information now can be considered common, so can leak, and we set his time interval. Assuming now that some time has passed, some delta t have expired, like this 2-1, so the counter has been decreased, and just user 3 is active. Assuming that user 2 comes again, its delta t time interval is expired, so it can be considered as a new user. We increment the counter, But since we are still under threshold, the information is considered private, so cannot leak. So this is the base of our algorithm, but our concern is to understand how this algorithm impacts the information that comes inside a given dataset. So we took some traces coming from an operational network, and we tried to apply this algorithm considering the different values of alpha and delta t. From this slide, as we can see, if we try to put the value of alpha equal to 2, we get the 75% of domains obfuscated. What does it mean? It means that the 75% of all the domains inside this dataset have been seen by less or equal 2 people, which seems quite a lot. But if we try to see this in a different perspective, so in the quantity of traffic that gets anonymization, if we try to still keep alpha equal to 2, the quantity of traffic that gets obfuscation is about the 10%. So most of the information that would be useful for further analysis are still kept inside the packets that we could keep thanks to this data collection. What's the lesson that we learned from here? The lesson is that the popular domain carry little sensitive information about the user, but they are responsible for the majority of the traffic inside the network. So, for example, if we get names like Google and Facebook, anyone goes to these kind of websites, so there are no concerns on the privacy of the different users. So letting this information by doesn't challenge any concern of privacy. So now this is the theoretical stuff. We took everything from there and we put it inside a practical tool and that can be used inside a given network. There are many requirements, as you could imagine, which are flexibility, first of all. It should support, obviously, the alpha anonymity because it is based on this concept. It should support the anonymization on all the protocol layer, should be scalable and deployable on high-speed links, and should support multiple legacy applications with different anonymization requirements. This seems quite confusing, maybe, but it will be easier to see this picture that can explain better the what is happening actually. Assuming that we have some networks with a splitter that gives the packets to a replier. The replier has just the ability of copying the packets to all the different consumers. But if we try, for example, substituting the replier with α-Mon, we can get many functionality. For example, first of all, we can have an unbounded number of input ports, so we can link many networks to the same device, but we can have also many output, an unbounded number of output, but each output can be configured differently according to the need of the machine that is at the bottom of this picture. Assuming, for example, that the security monitor needs a very low level of anonymization because maybe it's useful to see what is happening. A network monitoring maybe need a high level of anonymization because we would like to delete all the sensitive information because are not useful for the purpose of the network monitoring, and so on. So this is the concept of α-Mon and how it sits inside a given network. This tool has been implemented in a modular way because we would like to make it easy to be expanded. So we have a core system on which can be attached many blocks, which are easy to be put inside because just you need to write the code in order to manage a given protocol or a given layer and add it inside the central module of this system. Nowadays, this product is covering all the ISO-OSI protocol layer from layer 2 to layer 7, anonymized everything from the MAC address and IP address to the application level. Now I would like to show you why this tool is so powerful and how it performs in a real environment. So we took some traces from an operational network, and we have the Icp full, which represents a typical workload, Icp Adder, which is the same trace as before, basically, but we deprived all the packets of their payload, so we're trying to benchmark the packet capture. And finally, we have the DNS packet trace, which is based on just DNS traffic that has the aim on benchmarking the alpha-anonymity module. The testbed is quite easy and straightforward, so we have a traffic generator that keeps these traces and tries to send all the packets as fast as possible to the α-Mon machine that then sends to consumers the anonymized copy of a given packet. We try to give to α-Mon the highest speed as possible without having any sort of losses in the middle. At the end, we tried also to increase the number of consumers in order to see how the system performs by adding more computational concerns. Assuming that we have the simplest system of them all, so a generator and one consumer, with the use of just one core, thanks to our limitation of hardware, we could obtain just 10 gigabit per second anonymization. Obviously, this value drops if we try to increase the number of consumers at the end. For example, with the 2 consumers, it drops, but it needs just 3 calls in order to get the 10 gigabit benchmark. The same thing happens if we put 4 consumers. Obviously, in this case, we need 6 calls in order to achieve the 10 gigabits per second. But what we can see from this picture, and this is really interesting, is that the increase on power is linear to the increasing of the number of cores. So basically, by just adding more cores, we can achieve higher speed given the situation in which we fall. Then we get the Icp Adder. Obviously, here we have a drop in performance because since the packets are smaller, the number of packets that are analyzed in the unit of time is greater. So obviously, in this case, we need 5 cores to achieve the same performance as before. The same situation happens if we try to add more consumers at the end, but as we can see, the performance scales linearly with the addition of new cores. So probably by adding other cores, we could reach the 10 gigabit benchmark. A drop is also present in terms of the DNS, because obviously each packet should go through all the anonymization steps, which are really heavy. But obviously, in this situation, with just one core, we can hit the 0.66 gigabits per second, which is quite a remarkable result, by obtaining 3 gigabits per second with pure DNS traffic with 8 core, which is a quite remarkable achievement given what the system has to do. The drop obviously is present by adding new consumers, but the linear increase in performance is still there. So by adding cores, we are confident that we can reach higher speed and reach maybe the 10 gigabit benchmark that we saw at the beginning of this test session. So here I would like to draw some conclusions by wrapping up everything that I've presented to you. So α-Mon is a flexible and modular tool that can apply anonymization with a rich set of policies. It can provide anonymization to legacy monitors that need different traffic visibility. It is based on a streaming anonymization technique. It is scalable and efficient, and we had the possibility to test on a real environment this tool, since it is today active inside the Politecnico network. And today, actually, we are analyzing all the information that comes from α-Mon. So we are really happy that in this way, we are obtaining information about the traffic without training the privacy of the user that surf the Politecnico network. So I would like to thank you for your attention, and I would be really happy to answer any question. Thank you.
Thank you, Thomas, for your presentation. We have some questions from the public. The first is, what would it take to see this method apply in the real internet infrastructure?
Well, actually, the figure is quite straightforward. The system is ready to do that. Actually, now, because it's a project that has been developed inside Politecnico, we decided to put it first inside the Politecnico network. It is performing in an excellent way, so I don't see any concern in taking this tool and put it into a core network. It is already ready to do that, I mean.
So it's a free tool to use and ready to use
from now, yeah.
And the second question is, does the method only depend on the threshold and delta T parameters? Are these fixed on, do they adapt real time to the incoming traffic?
Okay, this is an interesting question. I went a bit over on this thing in order to be as comprehensible as possible. But the thing is that the system can be configured in all its sense. So it can configure in the number of input and output, in the how we apply anonymization. This is translated into the definition of alpha and delta T. Alpha and delta T can be configured by the user according to how much information the administrator want to keep. I mean, if you want to keep low information, then alpha should be a great value. Instead, if it is important for us to keep as little information, as little information as possible, we just need to vary the value of alpha according to this information. I can show you just a picture from the presentation that I showed you before. From this value of this plot, you can see that by varying the value of delta T, so the of alpha here, we increase and decrease the quantity of information that we want to keep. So it is the administrator that needs to understand, according to the final objective, what value of alpha and delta T to use. Of course, there are other papers that I wrote that are linked to this problem, but it's a matter of configuration that can be done easily by the user.
Okay, thank you, very clear. And I have one curiosity with the introduction of the GPR.
Yeah.
How much is important have a system able to maintain the security of our sensible data?
I mean, it's quite mandatory today. It is so important to prevent disinformation to leak. It's important not to keep disinformation in systems, for example, in hard disks or things that are permanent. It is important to let them be so volatile as possible. In fact, what we are doing here is just storing these values in a most volatile way, and in order to prevent this sort of leak, because there are many situations in which private information like names, addresses, and so on leak because the information systems of different companies are not, for example, well managed. And this is a really bad drawback in an era in which the digital information is so important. So I generally believe that it's important and maybe also mandatory from my point of view prevent all these situations.
Thank you, Thomas, and thank you also.
You're welcome.
So, if there are no more questions, we can proceed with the last part of the pitch. I would like to invite all the speakers to turn on the camera. Okay. Sorry, Eva, you can. Okay, thank you. Usually, at the end of each pitch, we give a certificate. In this case, it's a virtual certificate, but this certificate is a way to say thank you for your work, thank you for your research and for your time. So thank you, Stefano, Eva, and Thomas for the participation in this pitch. And also, I would like to say thank you for joining us using the YouTube platform, and I hope to see you in the next event, maybe in the in present. And that's all. So thank you, and have a nice evening, and goodbye.